Hi everyone, welcome to video number 2 for Module 3 of CNEED 7103 here at the University of Utah. Today we're going to be talking about the normal distribution and digging into some of the mathematical formalisms that actually specify the normal distribution. It's important to understand the actual underlying formula and the distribution itself because that's going to allow us to make very specific quantitative statements about the probability of certain events. So I like to say know thy distributions as a parody of the phrase know thyself, right? And in the same way that knowing thyself is a powerful thing that enables personal growth, knowing thy distributions is a powerful thing that allows us to make statistical judgments about the probability of certain events happening. Now, it's easy to feel a little bit lost in the weeds of some of these mathematical formalisms, and that's okay. But it's important that we dwell here for a little while so that we can really appreciate the power of what knowing a distribution allows us to do. Because if we can safely make an assumption that our data follow a certain distribution, then that allows us to make concrete statements about the probability of observing certain events. So for instance, assuming a normal distribution, what is the probability of observing a value greater than or equal to 1? Right? And the normal distribution is just one of several distributions that we'll discuss in this course, and one of several distributions that we want you to feel comfortable using and have a deep understanding of. But the normal distribution is particularly important, as we discussed in the previous lecture, and we're going to really focus on the normal distribution today. So the normal distribution, as a reminder, right, is a distribution in which most of the scores are clustered around the mean, and we have a high density of scores in that region. And then as we fan out in either the positive or negative direction, we have a lower density of scores, right? So we get this nice bell-shaped curve that you guys have probably heard about before. Mathematically speaking, that density function is defined as follows. So we have f of x, right? So for any given value, so x is going to be a string of values from, let's say, maybe if you go, you could really go from negative infinity to positive infinity, but for the sake of argument, let's just kind of constrain it. Let's say x goes from -4 to +4. So you're going to solve this for different values of x. So you're going to plug in maybe -4 the first time around, and then -3.9, then -3.8. And you could really solve this function for all of those different values in order to determine the density of scores at each of those values. So the first part, we have 1 divided by sigma, which is the population standard deviation, times 2 pi, which is a constant, right? And multiply that ratio times Euler's number, which is a constant, raised to the negative x minus mu. So x, again, is the value that we're plugging in. Mu is the population standard deviation, or the population mean. We're squaring that difference and then dividing it by 2 times the square of the standard deviation, or 2 times the population variance. Okay, so what we see here, right, is that we have pi and Euler's constant. So those are both constants and they're not going to change. X is going to change because it's the variable that we're evaluating this function over. Mu and sigma will be different for different populations, but within any given population, there is 1 mu and 1 sigma. In a standard normal distribution, mu is equal to 0 and sigma is equal to 1. So what we're evaluating really is the distance that a score is away from 0. So -4 would be 4 units away, -2 would be 2 units away. And normalizing that to what the standard deviation is, right? So in this case, if it's 1, 1 squared would be 1 times 2 would be 2, right? So the population mean and the population standard deviation are going to have an effect on this density function. And we can see those effects if we change mu and if we change sigma. So here we have 2 approximate standard normal curves. So I simulated these data, right? So these aren't perfectly normal, but these are based on sort of 10,000 simulated scores that follow an approximately normal distribution. So here we have different values of mu. In the first case, we have a standard normal distribution that's centered on 0, mu is equal to 0, and it has a standard deviation of 1, sigma is equal to 1. And you can see that most of those scores fall between +1 and -1. And very few scores are beyond +2 or -2. If we change the value of mu and we go from 0 to 1, so we're going from the solid line to the dashed line, you can see that now this distribution is centered on 1. So most of its scores now are actually between 0 and 2, because we go -1 standard deviation to the left, +1 standard deviation to the right. most of the scores here now fall between 0 and 2. And in fact, the same percentage of scores fall between 0 and 2 for this distribution as fall between -1 and 1 for this distribution. So changing the value of mu simply shifts this distribution to the left or the right. Conversely, changing the value of sigma changes the variability in the population. So here we have 3 different normal curves, right, that are all centered on mu. They all have the same population mean, but they have different standard deviations. If the standard deviation gets smaller, right, we go from 1 to 0.5, you can see this distribution gets tighter, which makes sense because if the standard deviation is getting smaller, that means the scores tend to cluster more closely around the mean. So we have a greater density of scores around the mean. Now, if the standard deviation gets bigger, you can see this means that the distribution fans out and the density of scores actually goes down, right? So now our standard deviation of 2, we have to go between -2 and +2 to get the same percentage of scores, to get the same density of scores that in the red distribution lies between -0.5 and +0.5. So changing the value of sigma changes the spread of the distribution, whereas changing the value of mu moves that distribution from left to right. So for any of these normal distributions, given the function, we can find the probability that a number lies in the specific range, because we can calculate the density of scores out of the total number of scores. So we can say, for instance, how many scores lie between -1 and +1, or how many scores are greater than +2. One tricky thing to think about here is that we can't find the probability of a score being exactly one value. And the reason for that is because technically, when we have continuous values, the probability of a score being, for instance, precisely 1 is equal to 0. And this is because for a truly continuous variable, 1 is going to be different from 0.99, and 1 is going to be different from 0.001, right? So the probability of something being exactly one value is impossible to determine, assuming we have infinite precision, right? And in a truly continuous case, that's an assumption that we make. So with infinite precision, the probability of something being exactly equal is going to be 0. However, we could, for instance, make a very narrow range and say, okay, well, what's the probability of a score being between 1 and 1.01? So this might seem like a bit of a limitation, that we can't say what's the probability of a score being exactly 1. But it's actually still very powerful because regardless of the distribution, as long as it's normal, right, for any different value of mu and sigma, we can actually say what percentage of that distribution is to the left of a number, or what's to the right of a number, or what's between two numbers. And to show you how that works, we can look at the following example. Okay, so we can take any given distribution based on its mu and sigma, and then we can look at any different score and calculate the probability associated with that value. So all normal distributions are going to be different, right? We said that the standard normal distribution has a mu of 0 and a sigma of 1, but mu and sigma could really be anything. So what we can do is we can transform any value. So let's say we have a variable y, and we're going to transform that into what we call a z-value or a z-score. And the z-score is a normalized score in which we take the value that we observe, right, the y, we subtract the population mean, and we divide by the population standard deviation. So we take y minus mu, and that tells us the distance it is from the mean, and divide by the standard deviation. Thus, if we have a standard normal distribution, right, and y is equal to 1, well, in a standard normal distribution, mu is equal to 0, sigma is equal to 1. So 1 minus 0 is 1, divided by 1 is 1. So the z-value for that score would be 1. It would be positive 1. It would be 1 standard deviation to the right of the mean. However, when mu is 0 and sigma is now 0.5, so this is still a normal distribution, but it's not the standard normal distribution, we would have 1 minus 0 is 1, divided by 0.5, that's 2. So this z-value would be 2 standard deviations to the right of the mean. So we can create z-scores which basically normalize our values to the standard deviation. So the z-score tells us is something to the left or the right of the mean in units of standard deviation. And from there, we can use the normal distribution density function to actually find the probability associated with any of those values. So once standardized, we can find the probability associated with any specific z value, right? So again, we take mu and sigma for each unique distribution into account, and then we can calculate these probabilities. And we could do this by integrating the density function, which we won't make you do by hand, right? We'll use some built-in functions in R to calculate these probabilities for continuous variables. We will make you do it by hand for discrete variables, for instance, like rolling a dice, in which case this calculation is a little bit easier. But for the continuous case, we'll just count on R to solve this problem for us. But conceptually, what we can do is we can say, okay, given a normal distribution, what's the probability of having a z-score less than or equal to -1? And that happens to be about 15.8%. And I've indicated that here with the dotted red line. And you can see to the left of that line, there's about 15.8% of the total density of scores. Now, what about being less than +1? Well, that happens to be about 84.1%. Okay, so I've indicated that here with the dotted blue line, and you can see that there's about 84% of the density of scores to the left of +1, and about 15% to the right. Now, what about the value between +1 and -1? Well, we can take the value to the left of +1 and subtract off the value to the left of -1, right, to isolate the value that's in the middle, and that happens to be about 68.3%. And again, regardless of the specific normal distribution that we're dealing with, for any normal distribution, 68.3% of the scores are going to fall between positive and -1 standard deviation. Okay. So an interesting thought experiment here is to consider, well, what would be the value exactly at the mean? Take a minute to think about that. Maybe pause the video, think about it for a second, look at these distributions, and think about what percentage lies to the left of the mean and what percentage lies to the right of the mean. All right, do you have an answer? Okay, so remember that our mean, right, and the way we calculate a z-score is going to be y minus mu. So if our value is the mean, that means y is equal to mu. So y minus mu is going to be 0, divided by the standard deviation is going to be 0. So we have a z-score of 0, which means it's right in the middle of our distribution, which means that a z-score of 0 divides our distribution neatly in half. So 50% of the distribution will be below a z-score of 0, and 50% of the distribution will be above a z-score of 0, which sort of fits, right? As you can see here, we're below 50% when we're to the left of 0. We're above 50% when we're to the right of 0, right? And if we did solve, in lab, we'll solve this exactly at 0, and we can see that that divides this distribution neatly in half so that 50% of the distribution is to the left of 0, and 50% of the normal distribution is to the right of a z-score of 0. So we're going to discuss how to calculate these probabilities in more detail for both normal and some non-normal distributions. But regardless of the specific distribution, the underlying lesson is the same, and this is what's really important. If we know the underlying distribution, or we're confident that we can make a reasonable assumption about the underlying distribution, we can make very explicit quantitative statements about the probability of observing an event. And this is what's really powerful as a decision-making tool in statistics, because we can start to say, given a certain set of assumptions, what's the probability of observing this event? And if that probability is very low, that makes it a statistically interesting event. And it might be worthy of further follow-up and more study.